Hi, welcome back. In the previous lectures, I've introduced NumPy module to address some of the limitation of a Python list and a Python array. In this lecture, I want to go a little bit deeper into NumPy. In particular, I want to describe how NumPy can address problems like memory fragmentation and also to look at support for vectorization. By the end of this lecture, we will be able to compare different Python array implementation, such as Python list, arrays, and NumPy arrays for vector and matrix operation that are the butter and bread of a high-performance computing. We will also be able to describe why NumPy has a higher performance than list and Python arrays, and we will be able to optimize the performance of the diffusion problem code using NumPy. As I said at the beginning of this lecture, we need to deal with some of the few issues when dealing with arrays in Python. One of those is really the fragmentation of the memory, the fact that we need to look up for reference many times, or the data is not in the caches. The other major problem was the support for vectorization. Luckily, NumPy, that is a Python module, has all these features. So it stores the data into contiguous big chunks of memory. So when we read the memory, it can grab a big chunk of data. And the second major point that it supports vectorization operation. So we can do multiple operation on vector elements. The NumPy name stands for numerical Python or numerical Python. Is very popular package. What does it do? Well, NumPy enriches the programming languages of Python with powerful data structures. Right? So the NumPy multidimensional arrays and matrices. As I said, one of the major advantages that any arithmetic that we do using NumPy arrays and matrices happens in chunks without having us to explicitly loop over each element. So we will express our operation as a vector operation, and this vector operation then will exploit vectorization that is available on our processors. Let's look at an example. So the example that I want to take to demonstrate the performance of different approaches when using different arrays implementation in Python is the square norm of a vector. So what is that? So let's take a vector with a certain number of elements. We take the vector, we multiply element by itself. So the first element with itself, the second elements by itself. And then we sum it up what is the results of this single element by element multiplication. This is nothing else than a dot operation or inner product operation between a vector and itself. Also is the square root of the norm of the vector. So if we want to take the norm or the amplitude of a vector, we take the dot product and then we take the square root. So what we're going to do is going to look at different implementation. Python list, we're going to look at two ways in Python wins. Just the classical with for loops, and the second one with the list is we're going to use a so-called list compression. So we're going to have two methods for comparing the performance of the list. We're going to have a methods that allow us to evaluate the performance of the array module in Python. And then we're going to have two implementation using NumPy arrays at the very end. So just to summarize, we're going to evaluate the performance of two implementation using list. One is normal one, the other one using the list compression, the other one with array modules, and we have two implementation using NumPy. One using just the vector element multiplication, and then we sum it up, and the other one just taking the dot product in NumPy. We are going to evaluate the performance using different array size. So on these slides I have just 1 million, but we can check how the variation of the performance change increasing the array size. And then we will see that we have a different way to allocate our vectors depending which kind of vector we do. The first one is the list, that we're going to use it. And then we're going to have an array that is using the array, right? So we're using array. Then we need to say which type is the array. So in this case is L, that stands for long. And then we use the same range, that is 1 million. Finally, we're going to use a NumPy array that can be defined in the following way. And what we're going to do is going to put timer. Yes, this is not very elegant way, as you know. There are much better way, but just for the purposes that I'm going to show that we want to time and compare the different performance. So this point in these slides, I present the performance. On the y-axis, we have the runtime, that is the execution time, expressed in millisecond. So that means that the higher is the worst. So higher execution time is not good, and the lower one is better. So going down, performance is much. And when we do on the x-axis, we have the vector length. So what is the size of the array? One things to notice is really that the scale here, we have a log scale here and a log scale here. We have as I told you, we have two different kind of list implementation. So this is the purple one, and the red one, the dash one, that is this one. And then you see here on the top, you have the blue, that is the array module. As you can see, all the performance using the Python list and Python array modules is pretty much the same. There is a little bit variability. It turns out that the list compression is technically the best among the three. Then way below, so we're talking about factor of between 10 and 100 in many cases. We have a difference of performance between Python list and NumPy array. As you can see here, the NumPy version is quite high performance. So if we want to get some numbers, so the simpler NumPy code runs 89 times faster than the non-square list. So when we use Python list, and roughly 80 times faster than the optimized Python list compression. We also note that the Python version with the list using list compression is slightly better than the normal Python implementation with the list. In the last lecture also we learned how to use the perf tool for assessing low-level profiling information on Linux machine. We can do the same for this particular case and comparing different versions. We saw that the list arrays are pretty much the same performance. That's why I'm putting here. And when using this kind of approach, and we monitor the perf tool, we get the number of instruction and the number of cache misses in percentage. We observe the following results. So list have a much higher number of instructions and also a much higher of cache miss, roughly 50%. When we use the NumPy version, we have a small number of instructions compared to the list. Basically, we have four orders of difference when it comes to the number of instruction. And when we use NumPy, the cache misses decrease to 20%. So to summarize these slides, so running each function using the perf tool, we see that the perf tool shows that the array and the pure Python function take about 10 to the 12 instruction, while the NumPy version takes about 10 to the 9. So NumPy takes way less instruction. In addition, the array and the pure Python version have 53% of cache misses against NumPy that has around 20%. So why NumPy gives us such a high performance when compared to Python list array? Well, the major reason, or one of the major reasons, is that NumPy has a very optimized C code that is being called by Python. And this code has been made specifically to take advantage of any vectorization that the CPU is enabled to. Some NumPy function use C Fortran HPC library. So these are very high performance libraries that are designed for specifically for solving some vector operation, some numerical operation. And a NumPy function accesses directly this C or Fortran HPC library from Python. I'm going to talk a little bit about this important HPC library in the last lectures, last two lectures of this module. So I recommend you to look at the final lecture of this module where I describe important HPC libraries such as BLAS. In fact, if you want to check which library your NumPy installation uses, you just import NumPy as an np, and then you use the command np dot show underscore config and parentheses, and it will give you which library the NumPy version is actually using for this high performance computing operation. I did this on my laptop, that is ARM processor, is the M1 ARM processor on a MacBook, and have installed the OpenBLAS. So all the operational NumPy are based on OpenBLAS library. I have to cut it out here, but so that I have also other library that NumPy is using. So if you want to check your library, remember your HPC library that you're using with NumPy, you can basically write down these Python commands in your IPython console. A major advantage, so there is the fact that these are optimized kernel in C, and also they are using some high performance library. The second performance optimization comes on how the arrays are represented in memories. Arrays are represented sequentially in memory as a low-level numerical types, so no heterogeneous one type and in contiguous space, so there is no jump around on different memories. Normal NumPy dot outperforms all the others approaches by quite substantial margin, so we saw quite a big difference. This is because of the specialization of the function that is just doing that operation. It is doing very fast, and also because we don't need to store the intermediate values of the vector. So this is an in place a kind of operation. By coming back later on with another lecture about the importance of doing in place operation in certain context for high performance computing. I show an example applied to calculate the square of a norm of a vector. So we take the vector, we multiply element by itself, and that's the square root, the square of the norm of this vector. What we want to do is to use NumPy on the exemplar code that we look at in the previous lecture, that is the diffusion problem code. It turns out that the only new functionality in order to make a vector operation in the diffusion code is the so-called roll function. You can check what is the description of the roll function online. But basically what this function does is the same thing as our modulo index string, right? We shift the vector and then we roll up on the other sides. So in essence, this operation of the shifting and the re-indexing. As on these slides, there is a very simple explanation on how it's working. First, we import NumPy as np, and then we have our initial vector, that is 1, 2, 3, and 4, and then we provide the shift, right? So in this case, we make a shift of this vector of one element. So if we do one element shift, the 3 goes here, the 2 goes here, the 1 go here, and the last one goes back in the beginning. So what we get as a result of this operation is the vector 4, 1, 2, and 3. We can do also on matrices. So we have if we have a matrices that is 1, 2, and 3, 4, 5, and 6, and then we say in this case how many elements we want to shift, and then also we want to say in which direction we want to perform the operation. So in this case, if you do this operation, you see that the shift is doing this way. So we shift only along one axis. We can embed in our diffusion code. So we are going to replace all those for loops in a very synthetic way. So we see that the contribution from different parts of the stencil on our grid now is coming from for parts where we do a shift of a +1 and -1 on the 0 axis, and then we have a shift of a +1 and -1 on the y on the on the axis equal to 1. And then we take care of the contribution coming from the central point when we calculated the second order derivative. Right? So this is a very synthetic, very concise way to express the Laplacian, that is the discretization of the second order derivative in x and in y. And we use this roll function that allow us to replace the loops with the vectors. After we introduce this function called Laplacian, we can basically replace the full evolved function by this simple line. So we see the code is much shorter, and the reasons for that NumPy here is really doing the hard work for us, so the vectorization part. What we are going to do is going to measure the performance counters, and we're going to use a perf as we learned in the previous lectures. If we run perf stat -e, and then we put all the different hardware counters, we got some interesting information. If we want to compare to the previous results of perf using Python list, we saw the most important thing is really the time. So here is roughly 140, here 17. We saw that a simple change to NumPy has a big effects on the total execution time, roughly 17 times speed up. The most important things when it comes to NumPy is vectorization. So vectorization is important. Although the NumPy version seems to be running fewer instructions per cycle, here we have in the Python list we have quite high instruction per cycle, 2.9. In the case of NumPy, we have only 1.07 instruction per cycle, right? So that's might be somehow counterintuitive. We would expect higher performance to have a higher instruction per cycle. So why this happen? Well, the reason for that is that yes, we are doing less instruction, but our instructions are much heavier because they are vectorized. So one vectorized instruction can multiply 4 or more numbers depending on the type in an array together, instead of requiring 4 independent multiplication of instruction. So in this case we have one instruction for doing one operation on the vector. So we have bigger instruction, but we have way less, and that's why we have a better total performance. Another important fact is really about the memory fragmentation and really about the memory problem. We see that in the case of the Python list, we have a cache miss around 50%. That's quite bad. When we look at the NumPy version, it's still not as good as we would like to, but is basically half of the cache misses that we have in the Python list code. So the NumPy version has reduced cache misses, 20% cache miss instead of sorry, here should be 28 cache miss instead of the 53. So roughly a factor of 2 better. A cache miss is slow down computation because the CPU must wait for the data to be retrieved from the slower memory. So we need to wait for the memory. And memory fragmentation, it is a dominant factor in performance. Again, I want to repeat and stress this out many times in this course. Memory issues are a dominant factor in slowing down our code. Often we think that is computation. No, most of the time is really memory issues. So computers have in fact very well designed to do exactly the calculation they're requesting them to do, but memory is the bottleneck. So the bottleneck is getting those numbers to the CPU fast enough to see that the calculation can also be super fast. I want to mention this excellent book about NumPy, structured data layout in memory, and also including some optimization technique, for instance, how to express certain algorithm using a vectorization technique. So if you're very much interested in this topic, I highly recommend it to check it out. Check this book out. It is open source. This is the last slides of this lecture. To summarize, the NumPy implementation performs best in our codes with arrays and matrices. This is because of two factors. The first one, support for the vectorization, and another one is addressing the memory fragmentation problem. So we read in big chunks. Lastly, we can expect performance improvements of 5 times to 100 times faster using NumPy arrays. Of course, this really depends on the problem, the problem size, and underlying data structure. And this performance improvements is of course against list and Python arrays. This is the last slides, and talk to you soon.